In the previous video lecture, we have seen about minimum mode and maximum mode of 8086 microprocessor. So in this video lecture, we are going to see about interrupts of 8086 microprocessor. So before we start off with the interrupts, just recollect what is interrupt. So this we have discussed in while we are seeing in the 8085 microprocessor. So what's an interrupt? So it's nothing but a signal or an external signal. Okay, it might be an internal or external signal that disturbs the normal execution of the main program. So this we have seen in 8085 microprocessor. So what will happen when an interrupt occurs? So the processor immediately stops the current execution of the main program and jump on to the interrupt subroutine, which is nothing but the ISR, which is nothing but the interrupt program, right? So it will execute the interrupt program and then it will return to the main program. So before the processor jumps to the ISR, so what it will do, it will store the status of the main program, nothing but the PC value, program counter value, then the status of the program, which is nothing but the flag register values, and then the general purpose and special purpose registers values into the stack, and then it will jump on to the subroutine, execute it, and it will return to the main program after retrieving all this data from the stack. So this is what will happen when an interrupt occurs. Okay, so as of there in 85, in 86 also the same thing will happen. So before we see what all the interrupts are there in 86, we will see what will happen when an interrupt occurs. Fine. So this is your memory. Fine. And consider that you have your main program. Okay. So while executing the main program, the interrupt occurs. Fine. So when the interrupt occurs, it's supposed to jump to the ISR. Okay, so before that it will store the value of PSW, which is nothing but program status word. Fine, this is nothing but your values of the flag register, then the main program's code segment value and the main program's instruction pointer value into the stack. So this is your stack segment. Okay, so the first value, so stack segment, then stack pointer. So stack segment will give you the starting address of the stack memory and stack pointer will give you the offset value. Fine. Do you remember what is offset address? Yes, we have discussed in the architecture itself. Okay. The value first, the program status word, nothing but the flag register value will get stored in the stack. Then code segment value will be stored after to the stack program status word. Fine. So this program status word is of 16-bit, so it will take 2 bytes of memory. Fine. So that's why SP -2, where your code segment value will be stored. So this is also a 16-bit value, so it occupies 2 bytes of memory. Okay. So then the IP value, instruction pointer value, will be stored, which is not where means SP -4, since the code segment will occupy 2 bytes of memory. Okay, so the code segment will have the starting address of the code segment and then IP, which is nothing but instruction pointer, which will have the address of the next location. Fine. Okay, that will be stored first. Then what will happen, the program, okay, so all those status registers, code segment and the IP values will be stored in the stack. Then what the processor will do is, it will determine what interrupt has been occurred. So since it's having 256 types of memory, it will determine what type of memory has been occurred. So once the type of memory has been occurred, it will look into the ISR's address. Okay, so ISR's address is nothing but its code segment value and IP value, that will be determined. So these values, code segments, ISR's code segment value and IP value is stored in the interrupt vector table. Fine. So all these types of interrupts, 256 interrupts, which is having its corresponding code segment value and IP value. So this is stored in the interrupt vector table. So once these registers values are stored inside the stack, the processor will determine the type of the interrupt. Then it will go to the vector table where it can locate its corresponding code segment and the IP value. Fine. So here this is the interrupt vector table. So where the interrupts code segment and IP value will be stored. For each interrupt will have 4 bytes of memory. Since the code segment is 16-bit, IP value is 16-bit. Okay, so each interrupt will have a code segment value and IP value which will occupy 2 bytes and 2 bytes, a totally of 4 bytes of memory to store the data or the value of one ISR. Fine. So if 256 memories, so it will occupy 4 bytes of memory. Each 250 totally 256 interrupts, which each and every interrupt will occupy 4 bytes of memory. Fine. So that will have the code segment and IP value. Fine. So this is a vector table. From here to here we have the vector table. So this value is nothing but CS and this value is nothing but IP. That will be stored here. We will take this value out and your processor goes to this specific location, goes to the code segment. You will have your, if this is your memory, if this part is your code segment, fine. So this will give you the code segment starting address, if suppose 2000, that is the value, and IP is nothing but the offset value in between. If it is 2356, so then 2000 is to 2356. Your processor will jump into this location where your ISR, nothing but interrupt service routine, your interrupt program will be stored. From there the program will start its execution. Fine. So this program will be executed until it's find the return instruction, which is nothing but interrupt return. Once the process sees to this interrupt return instruction, it will again return to the main program where it has been stopped its execution. Fine. So how it returns to the main program? So once the process sees this interrupt return instruction, it will move on to the stack memory, okay, where we have stored the PSW, CS and IP value. Okay, so once it sees to the interrupt return instruction, it will move on to the stack. So takes the value from the stack, flag register, code segment, IP value, it will take from the stack and restores in the same register and continues its execution. So this is what will happen when an interrupt occurs. Fine. So as we have discussed already in 85, the two types of interrupts are non-maskable interrupt, maskable interrupt. So this you know already. So non-maskable interrupt, we cannot mask it, we cannot stop the execution of those interrupts when it has been occurred. So those kind of interrupts are called non-maskable interrupts. So maskable interrupts, even when an interrupt, such kind of maskable interrupts occurred, so we can stop its execution by enabling and disabling such kind of interrupts. So those kind of interrupts are called maskable interrupts. Fine. So as of these types, we are having another type, that is external interrupt, internal interrupt. Okay. So the external interrupt that we will give by through an hardware. Fine. So here we are having two external interrupt. One is NMI, another one is INTR. So NMI is nothing but non-maskable interrupt. So INTR is nothing but interrupt request. Okay. So these are all the two external interrupt that is available as a pin with the 8086 microprocessor, through which we can connect any of the devices to signal to trigger the external interrupt. Fine. Then internal interrupt. So this is all nothing but that we'll give when we write the program itself. Fine. So usually we will write the program. In the program itself, we will include the software interrupts that are nothing but internal interrupts. Okay, so those kind of interrupts would be divide by zero, then single step interrupt. Okay, those kind of interrupts are software interrupts. Fine, that is nothing but internal interrupts. So what is divide by zero? So if we divide a number by zero, obviously we will get an infinite value. Okay, fine. That is not possible. No, we can't divide a number by zero. So that kind of situations are known as interrupt. Okay, if you want to signal those kind of situations to the processor, when you divide a number by zero, the processor by itself will generate a signal to notify that these kind of things cannot happen. Okay, so those kind of maskable and non-maskable interrupts, external and internal interrupts, we are going to see it now. So as we have seen, the hardware or external interrupts are NMI, interrupt request, then trap, it's a kind of an interrupt, I will tell you. Then internal or maskable interrupts are from type 0 to type FF. Okay, totally 0 to FF, 256 interrupts are there. Fine. So this is what the interrupt cycle. Fine. So as you have seen already here, so this is the interrupt vector table, where each and every interrupt will have its code segment value and IP value that is stored in a memory, that is called as interrupt vector table. Fine. So since we have type 0 to type FF, which is nothing but 0 to FF, 256 interrupt, each such interrupt is occupying a memory of 4 bytes. Fine, 2 bytes for IP and 2 bytes for CS. So type 0, which is nothing but divide by 0, the address from this is the code segment address, and this is the IP address. Okay, 00 to 02, it occupies the memory. Fine, IP CS, that is reserved for type 0. The next interrupt will start from 04 and 06, so that will occupy the memory, is given for type 1, which is nothing but single step interrupt, which is nothing but trap. Okay, then type 2 interrupt, which is nothing but NMI, its address starts from 08 and ends in 0A. Okay, so the next is interrupt single byte instruction. Okay, this is included as a software interrupt. This is an instruction through which we can give an interrupt. Okay, this is type number 3. So such kind of table is allotted from 00 to FF. Each and every memory is having a separate code segment and IP value that is stored in an interrupt vector table. So once an interrupt occurs, after storing the values in the stack, code segment value, IP value, FR value of the main program into the stack, the processor will look on to the interrupt vector table, takes the corresponding IP and CS value, store it in the code segment and IP register in the processor, continues its execution. After it sees the interrupt written, then it will again look into the stack, retrieves the main program's values, then continues with the main program execution. Okay, so this is what will happen when an interrupt occurs in 8086 microprocessor.